What's up, everybody? Welcome back. We're getting started on homework 5 today. This should be a fairly quick one, but it's going to be separated into 2 parts. The first part here, we're going to talk about something called drag coefficient, okay? And as you'll see in the video, drag coefficient is highly dependent on the Reynolds number for our particle traveling through a fluid. So the problem statement we have here laid out before us. Let's read it. It says the drag coefficient for smooth spheres has been fitted to experimental data using the following correlation. Okay, and then finally we get here, I'm not going to read all this, but this is the value for the drag coefficient, C sub D, and it's equal to all this. And we want to create a log-log plot of the drag coefficients as a function of Reynolds numbers and explain qualitatively the steep drop in drag coefficient at a Reynolds number of approximately 300,000. So we should expect to see that drop around 300,000 in our diagram. So let's get started. The first thing we'll need to do, obviously, and as always, import our NumPy, make our operations a little easier. And then we're going to make a chart. So I'm going to use Plotly. I'll say from plotly.subplots. We want to import make underscore subplots. There we go. All right. And it should be pretty quick to do this. All we needed to do is define a function for our drag coefficient. So we'll call it CD, just like in the problem statement. And it's going to be dependent only on one variable, and that's Reynolds number. As we know, our Reynolds number is dependent on a lot of things, but out of this function, we're going to want to return basically our drag coefficient as we see it here. So actually, it's going to be pretty easy. All we have to do is copy and paste this kind of information right in here. So I'm going to say this, put it in here. I'm going to take this coefficient that they gave us from the data and put it in here. And this one. And then finally, we want to return this value. Okay, that's pretty simple. Okay, so what Reynolds numbers do we want to try? Well, let's go ahead and do quite a few of them. So I'm just going to say we're going to create a log space for these. Yeah, we'll say from, I don't know, 10 all the way up to this, like 7 zeros is 10 million or something like that. Do that step there. Okay. And then I guess we want to use those numbers as our Reynolds number values. So we want to say, let's do our CD, we'll call these our CD values, are going to equal CD of X, basically. Okay. And now we can make our plot. So all we will need to do is we'll call this figure equals, just do make underscore subplots. Okay. And then we'll need to add, always do that wrong. Big dot add scatter. And we're going to want our X values, our Y values as our CD values, yeah. Evals. And then we'll put this in line mode. Okay, and then we can do a quick update. We want a log plot, it says, so fig dot update underscore layout. And we want to do, oh, actually, that's the wrong command. What am I thinking? Update underscore. We're going to do x-axis first. And we'll do this as type is equal to a log scale. Same for the y-axis. Fig.update underscore y-axis. Type equals log. I'm sure you could do those at the same time, but I'm not going to mess with it. And finally, we can do an update layout to make this look a little prettier. And do big.update underscore layout. We'll do width equals 800, height as, let's do 800 as well. Well, let's do like 600. That'll fit on the screen. And finally, we can do it in dark mode. So template equals plotly underscore dark. Okay, shift enter. All right, appears I've done something wrong here. Okay, so it appears I just forgot to put our parentheses there after make subplots. Now it should import that from Plotly correctly, and let's see what we get. Okay, so you can see the plot we obtain here. This shows our drag coefficient as a function of Reynolds numbers. And just like we saw in the problem statement, there is a steep drop in drag coefficient at Reynolds numbers about 300,000, which is right about here. So this is really, really steep drop here. Now, why is that? Well, that's a complicated question, but let's go ahead and open snipping tool and my favorite tool, and we can solve this, figure this out. Okay, so let's put this over here, put this over here, so you can see our chart. Okay, so why are we getting a steep drop here? Well, let's draw a picture. So we have a ball. Let's say we have a ball, and it's traveling through the air. And so the airs are fluid in this case, and you can see some, here's going to be like the air flowing around it, right? This drawing's not perfect, but you get some air flowing around it. Now, when this ball is going really fast, we get this air has to go around the surface of the ball, and it comes back down and over, right? And compared to, say, just a streamline of air on top of the ball outside of the surface, the boundary, this air particle has to travel a further distance than this one, right? And so what happens is by the time that the air travels around, it can't quite fill the space behind the ball as fast as the space in front of the ball is filled. So what you have is a high pressure region in front of the ball and a low pressure region in behind the ball, right? And because you have a high pressure region here and a low pressure region here, over the cross section of the ball, over this cross section of the ball, we get a drag force. And this is the drag force. We call this form drag. Okay? And that's effectively what comprises it's the most dominant form of drag on the surface. There's also skin drag, but it's pretty negligible compared to this form drag. Okay, so why is it that we get an extreme drop in this drag force when we get a Reynolds number high enough? Well, we know that the Reynolds number, RE, is equal to rho VD over mu. And if you remember from a few videos ago, we plotted a Moody diagram and we talked about the Reynolds number and the different regimes of flow. There's turbulent flow and laminar flow. Well, what happens is when you get to a Reynolds number of about 300,000, you achieve a flow that is turbulent, and it helps carry air down into the void, and it creates a higher low pressure region. So you can almost imagine this. Let me draw it a little bit bigger. That as the air comes over the ball, okay, and you're in a turbulent regime of flow, you almost get these swirls. We've kind of seen them behind the ball, right? And it helps drag air from the streamlines above down into the void. What this effectively does is creates a higher low pressure region behind the ball, and so you have a less difference in pressure over the same area. Because of this smaller difference in pressure, you have a smaller drag force, and that's what this big drop in drag is. Now, eventually this drag does come back up. The drag coefficient does come back up, but that's what causes this, qualitatively speaking, right here. Okay, so I think that is sufficient for this first part of the problem. I'm going to go ahead and set up part two of this problem, and it's going to be an application of this on a soccer ball. So stick around and we'll get right to it. What's up, everybody? Welcome back. We're going to get right back to it with this problem. So we've just created, oh, and by the way, sorry for the change of sceneries. I had to move rooms. So you're in my basement now. Got you still right here behind me, and it's my workspace, and right here in front of me, and we're gonna keep working. So we just calculated, or rather displayed our diagram for drag coefficient versus Reynolds number, and now what we're going to do is put some numbers to this and use it in the actual problem. So here's the problem we get. It says calculate and plot the trajectory of a soccer ball launched at 70 miles per hour at an angle of 30 degrees to the horizontal until its first bounce using the above correlation to account for the drag force. Assuming the ground is horizontal, how far does the soccer ball travel before its first bounce? Okay, so we've got a few things to do here. Um, some things I've added in here already just for us. Obviously, the fluid we're kicking the ball through is air on our scenario. And that being said, the values for density and viscosity of air are as follows. And then I did look up the average diameter and mass of soccer balls, and these are the numbers I got. So those are the numbers we're going to be using for this video. So let's get right into it. We're going to use those first and foremost. Um, so I might as well just copy and paste these in here for the code. All right. And then additionally, we'll need gravity. I don't remember if I put this one in here already. I don't think I did. And we'll need the area, the cross-sectional area of the ball. Okay, so call that A, and that's going to be equal to MP pi. I'm going to move this a little bit closer to me. NP dot pi times d squared over 4. Okay, great. Now, let's talk about where this ball is at, what's going on here. So we've got a few things to note. This is going to be an initial value problem, meaning we'll need to import the solve IVP from SciPy. So let's go ahead and do that. So from uh, SciPy.integrate import solve IVP. And additionally, we have we need to know our kind of initial values for the problem. So let's talk about position and talk about velocity. So at time equals 0, first of all, we know that we have a position, an x position of 0, and a y position of 0. So I'm going to define those now as px0, 0, py0 is 0, and then we have a v initial, okay? And we're given that as 70 miles per hour. Okay, so 70 miles per hour, we need to convert that to meters per second since we're using our standard metric SI units. So I went ahead and looked up the conversion here. 1 mile per hour, if you didn't know, is 0.447 meters per second. Okay, there's that. And then we should probably break that down into x and y components as well. So we need a Vx naught and a Vy naught. Okay. Before we do that, we obviously need the angle that the ball is being kicked at. So call that theta. And that's going to be 30 degrees. Again, we want to convert that into radians. So 30 degrees times, there is 2 pi radians in 360 degrees, or pi radians in 180 degrees. So we can do mp dot pi over 180. That should give us our angle in radians. That being said, we can now calculate Vx naught and Vy naught. So Vx naught, right, is going to be V naught times, and our x value, if you think about our angle, cosine, right? E dot cosine of theta naught. And then our Vy naught is V naught times NP dot sine of theta naught. Okay. I apologize for the noise in the background. If you can hear that, is our water meter ticking. Okay. So I think that's a good place for us to start. And the next thing we'll need to do is define a function. It will be dependent on time and a vector, which describes the position in the x and y direction and the velocity in x and y direction of the ball at any given time. Okay, so we'll just say quickly px, py, vx, and vy. That's this vector. Okay. Now, v at any given time is simply the square root of the sum of the squares of Vx and Vy, right? It's just Pythagorean theorem. You have a velocity in the x direction, a velocity in the y direction. The total velocity is the square root of the sum of the squares. So V equals mp dot, I believe it's square root, yep, of Vx squared plus Vy squared. Okay, the next things we'll have to define are Reynolds number, which are simply, as we've discussed before, rho times V times D over mu. And next we'll want the drag force on the ball. The drag force obviously is related to the drag coefficient, which is a function of Re. And through some force balance equations that I won't derive here, but maybe in a later video, is equal to the drag force is equal to the drag coefficient times A times rho times V squared over 2. Okay. Now we're doing all of this to return following. We want to return effectively the integrals of the of the vector. Okay, so we want to have not only the position and velocities, we want to have the now velocities and accelerations of the values here. Okay, so the position in the x, position in the y, obviously those are pretty easy. They become uh, Vx and Vy. Okay, but the accelerations are a little bit harder. So I'm going to pull up our handy dandy software used by the CIA, also known as the snipping tool. And if I can get this to come over here, can I get this to come over here? Um, let's see. Close. See if I can open that again. Okay, here we go. For some reason, it was getting stuck before. So if we have our ball right? And maybe it's moving in this, oops, in this direction, right? The drag forces on the ball are always going to oppose the direction of the ball's travel, no matter which direction it's traveling, right? And so let's think about what forces and then therefore what accelerations are on this ball. Well, in the uh, we have some component of this drag force in the x direction. We have some component of this drag force in the y direction, and we also have gravity in the y direction acting on the ball at any given time. So let's first and foremost talk about this drag force in the x direction. Well, if we wanted the acceleration that is caused by the drag force in the x direction, it's pretty simple. We just take the drag force over the mass, and then since the total force here is in the same but opposite direction as the uh, force that's moving the ball, we can simply scale it by the same basically ratio between the x direction and the total magnitude of the vector. So what that looks like then is Vx over V, right? It's moving in the same the force the drag force on the ball is in the same direction but opposite as the velocity vector, right? So that's all we're doing here. This is equal to the acceleration in the x direction, okay? Now the acceleration in the y direction, very similar. It equals minus, this is our, by the way, this F, right, is our drag force F over m scaled to the y direction. But then we also have to take into account gravity, okay? So these two things are the last two things we want to return in our vector, and I'm just inputting them in the same order as our vector up here. So Vx first, we have negative F over m times Vx over V, I can type a V, and then we have negative F over m times Vy over V, right? And then minus G. Okay, I'm gonna close our snip here. Can I get this back, please? There we go. Okay, and that's what we want to return from uh, our function here. Okay, next we're going to define an event called, let's say, hit ground. Okay, again, it's dependent on the time and the values of that vector. Okay, and when we call this vector, we want to return the x position of the vector. So, or sorry, when we call this function, we want to return the first value of the vector, right? The x position. So we know where the ball's at. Okay, next we'll need this in here. Okay, and that hit ground dot direction is -1 because when the ball's traveling back down to the ground, it'll be passing basically from, it'll be going from positive to a negative value for y, right? And now we can start plotting. So we should guess first a value for time end. I'll guess 10 seconds. Probably wouldn't take that long, but and then we can do our result is equal to solve IVP. We need our function, which is right side. We're going from 0 to t end. Our initial values are the x naught. Actually, we have to do this in the same order. So we did px naught, py naught, vx naught, and vy naught. Our events hit ground, and dense output equals true. Okay, great. Next, we can start our plot. Okay, so for our plot of time, we are going to want linspace 0 to res.t events 0, 0. What this is going to do is make our plot perfectly spaced, is what this is going to do. 100 increments. Okay. And then we need equals res.sol t plot. Okay. And now we can execute the make subplots command that we've already imported. We'll call this figure 2. Okay. For our x values, we want the x plots, right? And for our y values, we want the py plots. Oh, there we go, py plot. And for mode, let's do markers. Okay. We can then do an update. Oh, fig2. Come on. Fig2 dot update. Layout. We're gonna do width. Oh, I missed an underscore here. Let's see what we get now. And I took away the S. Okay, and I put it in the wrong place. Shift enter, come on. There we go. Okay, so here we get a plot of our soccer ball. You can see it's not a perfect parabola. That's because of that drag force acting on the ball, pushing it back a little bit as it slows down. And it looks like when it reaches the ground here, it's at about almost 60 meters. So it goes pretty far. This isn't to scale, the X and Y axis to scale. Obviously, it goes much like shallower, so I guess we can fix that here. So I guess you can do fig2 dot update Y axes. We can do scale anchor equals X and scale ratio equals 1. Let's try that. Okay, and that's a little bit better there. So that's the scaled version there. And we can see there's our trajectory of our ball. It reaches 59.60 meters when it reaches the ground. So I think we've done all we can. That is the solution to the second part of this problem. Assuming the ground is horizontal, how far does the soccer ball travel? 59.6 meters. And I think we're good. There's our trajectory path. All right, thanks for joining me on this video. We'll see you next time.